In the last two chapters, we established the concept of heat, internal energy, and work in a gas system. We learned how these quantities are parameterized by pressure, volume, and temperature, which describe the macroscopic states of the system. The macroscopic state of the system is described by the kinetic energy of the constituent gas particles in the system. We are now ready to put everything together in this so-called first law of thermodynamics. Mathematically, it is written in the following equation. What it means, now you listen to me carefully. Recall back those simulations I showed you in the last 3 videos. Gas particles are zipping and bouncing around in a container. Then we heated the container. What did you actually do when you heat the container? Well, you supply heat energy into the system, didn't you? Where did this energy go to? It was absorbed by the gas particles, increasing its kinetic energy, if you think of it in terms of the individual gas particle. But if you think of the system as a whole, this heat went to increase the internal energy of the system. This was signified by the increase in temperature. The particles were now getting more energetic, and they started pounding the container's wall harder. Eventually, they drove the wall away, and we said the gas was doing work on the wall. Thus, first law of thermodynamics in plain English says, the amount of heat supplied into a gas system will be converted to increase the internal energy of the system and the work done by the gas. Depending on the sign of the quantities, different ways to write this equation may arise. Nonetheless, if you think about it, isn't first law of thermodynamics the conservation law of energy? The heat energy that comes in will have to be accounted somewhere. It won't just disappear to oblivion. It is accounted in the form of internal energy of the gas, and if it happens that the gas also expands in the process, it is also accounted in terms of the mechanical work that the gas has done. On the other hand, if heat energy flows out of the system, this heat will not have just appeared out of nowhere. It has to come from either the decrease in internal energy of the system, which means the gas is cooling down, or it is contracting. Either way, energy of the whole system is conserved. This is the essential theme of this particular lecture video I would like to bring up. What is going to happen next, we will apply this one equation in different thermodynamical processes we have learned earlier. We shall start with the process whereby n moles of gas is heated at constant pressure. The technical term to refer to this process is isobaric. Iso means equal, baric means pressure. Hence, isobaric literally means equal or constant pressure. The PV diagram of an isobaric heating is shown here. Since pressure is constant, the increase in temperature is accompanied by the increase in volume, as governed by Joule's law. The work done by the gas during isobaric expansion has been derived in the last lecture video. That is, pressure times the change in volume, or pressure times final volume minus initial volume. I use subscript F and I to refer to the final and initial state respectively. Or if you wish, you can also recast the equation in terms of the change in temperature using ideal gas equation. The change in internal energy is given by the equation we derived in lecture 11.2, 3/2 N times R times delta T. Here, and for the rest of this chapter, we shall assume that we are only dealing with monoatomic gas particles, so that we can ignore any complication which may come from the extra mode of motion that become more apparent at higher temperature. The heat supplied to the system during this process, as given by the first law of thermodynamics, is the sum of change in internal energy and the work done by the expanding gas, which is 5/2 times number of molecules N times universal gas constant R times change in temperature delta T. How about heating n moles of gas at constant volume, of which PV diagram is presented here? Such process carries a technical name isochoric or isovolumetric. In this case, the increase in temperature is accompanied by the increase in pressure as governed by Gay-Lussac's law. As you can see from the PV diagram, isochoric heating involves no work at all, because by definition, isochoric process does not involve change in volume. The gas particles are pounding on the walls of the container. The exerting forces on the walls, no doubt, but they do not drive the wall. If there is no wall displacement, then there is no work done on the wall as we learned in lecture 6. Consequently, by the first law of thermodynamics, the heat supply during an isochoric process will be absorbed to increase the internal energy of the gas system, which is given by 3/2 times N times R times delta T as derived in lecture 11.2. So from these two processes, isobaric and isochoric, we thus learn that there are two ways to heat a gas system. First, we can heat the gas at constant pressure. The amount of heat required to do so is computed in slide 2, 5/2 N R delta T. Alternatively, we can heat the gas at constant volume. The amount of heat required to do so is computed in slide 3, 3/2 N R delta T. Now suppose you are cooking Maggi mee. To cook Maggi mee, you need to boil the water first. How do you speed up the boiling? Well, you can use bigger fire for obvious reason. But if you are very concerned about your gas bill, can you still speed up the boiling without resorting to bigger fire? Well, you can. Cover the pan. Your mom might have taught you that. Covering the pan is akin to fixing the volume of the container, the saucepan, as you are heating it. As you can see from this equation, for the same increase in temperature delta T, it actually takes lesser amount of energy to heat the gas at constant volume than to heat the gas at constant pressure. The ratio is 3/2 to 5/2 to the advantage of isochronic heating in this regard. But, sir, your last question is on water. This slide is about gas. Are they the same? You may wonder. You are absolutely right. Liquid and gas are not the same, but the concept that material heats up faster when kept at constant volume than it does when kept at constant pressure is generally true. An alternative way to understand this phenomena is through the first law of thermodynamics itself. In isochronic heating, since the process involves no work, the amount of heat supply is solely used to increase the internal energy of the system. It is thus a very focused effort. Meanwhile, in isobaric heating, the amount of heat supplied is spread to increase the internal energy of the system as well as to do mechanical work. However, regardless of the process, whether it is isochronic or isobaric heating, the increase in internal energy has to be the same if we want to increase the temperature of both systems by the same amount too. Remember, when we were deriving the equation for internal energy, the change in internal energy depends only on the change in temperature and not the process that happens in between the final and initial temperature. So you can imagine that to increase the temperature of the two systems by the same amount, that is to say to increase the internal energy of the system by the same amount, we definitely have to supply more heat in isobaric heating. This extra heat is actually used by the gas to drive the wall of the container eventually. The second thing I want you guys to note from these two equations is their similarity to the equation Q equal to M times C times delta T we learned in lecture 10 on phase transition. In fact, they are interchangeable. This is obvious when we are talking about heating a material in its gaseous state at the extreme right of the phase transition diagram. We can equate MC delta T to 3/2 or 5/2 depending whether we are heating the gas isobarically or isochorically, and R delta T. Of course, we need to apply some conversion in the process. For instance, we need to be able to find out the mass of so and so mole of, say, argon gas. To do so, we need to know the molar mass of the mentioned gas, but that sort of information can easily be found. More importantly, the physical meaning of these equations are the same. The amount of heat required to heat the gas depends on the amount of the gas, be it in terms of mass or mole, the increase in temperature, delta T, and a sort of constant. In lecture 11, we call this constant heat capacity. Hence, we shall also refer to this constant gas heat capacities. The difference is that in solid or even liquid, we typically deal with only one type of heat capacity. The difference in the amount of heat required to heat a solid or a liquid at constant pressure versus heating at constant volume, as far as daily material and daily temperature range are concerned, can be ignored. It is not so with gas. There is significant difference in the amount of heat required to heat a gas at constant pressure versus heating at constant volume. This difference gives rise to two different types of gas heat capacities, identified by the subscript P or V, heat capacity at constant pressure versus heat capacity at constant volume. As you can see, the heat capacity at constant pressure is larger than heat capacity at constant volume. This implies, in accordance to the physical meaning of heat capacities, it takes more energy to heat a material at constant pressure than to heat the same material at constant volume by the same increase in temperature. Lastly, we have isothermic, a thermodynamic process whereby temperature is kept constant, whose PV diagram is shown here in accordance to Boyle's law. Because the process involves no change in temperature, that is to say, final temperature is the same as initial temperature, the change in internal energy is zero. Once again, remember that the change in internal energy only depends on the change in temperature. No change in temperature means no change in internal energy, full stop. So from the first law of thermodynamics, the work done by the gas to expand the container must be equal to the heat supplied to the system. So this probably sounds like a paradox because essentially you are heating the system, yet the temperature of the system does not increase, unlike in the previous case of isobaric or isochoric heating. Well, I guess it sounds paradoxical to us because our everyday life understanding equates heating to increase in temperature. But in physics, heating an object does not necessarily increase the temperature of the object. We learned this before when we learned phase transition in lecture 11.2. During phase change from ice to water, for instance, the heat provided does not cause the temperature of ice-water system to change. It stays at 0 degrees Celsius. In this context, the heat supplied to the system all goes into mechanical work. How do we then compute this mechanical work? We have the equation pressure times change in volume. However, like what we discussed in the last lecture video, pressure in isothermic process is not constant, so we have no choice but to resort to integration to compute this work. We are integrating pressure of a change in volume, so the key in solving this integration is to rewrite pressure as a function of volume. We can do so by recalling the ideal gas equation. Notice that N times R times T is a constant factor, since T is conserved in isothermic process. We can thus take this out of the integration and simply integrating 1 over V over dV with the limit of integration goes from the initial volume Vi to the final volume Vf. The outcome of the integration is given by the natural logarithm of final volume over initial volume. If you have no idea at all what I was talking about for the last couple of minutes because of your lack of calculus background, never mind. We can have a separate discussion over this offline. Or else, you can simply put your faith on me that this calculation is correct and simply take the final result as the work done in isothermic gas expansion. We still have one more thermodynamic process to study, but let's conclude this lecture video for now. I would actually recommend you guys to rewind this video one more time before proceeding to the next lecture video on adiabatic process.